Last week we did this deep dive into radiation, and we explored the different types of radiation, what those radiations are actually made of, why radiation happens, why is it that a nucleus is unstable to begin with and releases these forms of radiation. This week we're applying all that stuff that we know about radiation to the question of what biological impacts does this radiation have on biological systems? In other words, how does this radiation interact with cells and the molecules that make us up in such a way that on the one hand, it could have devastating, harmful consequences to human beings, and on the other hand, it could be used as a tool to fight, let's say, cancer, okay? So that leads us to this question of why do we care? And I've already hinted at it, which is that there is something very compelling and remarkable about radiation in the sense that it is this substance that most of us have heard of, but it's completely invisible. And yet, many of us have seen pictures from, say, the Chernobyl disaster, or in some way we've seen pictures of radiation burns. And you can see the absolutely devastating effects of this stuff. And yet it's something that we can't see. And that creates this kind of mystery. I remember I was a young boy when the Chernobyl accident happened. And it felt like this strange kind of magic, almost like a spell had been cast in the air that was harming all these people and this livestock and these plants and water systems. And yet it was this completely invisible thing. And so now the other kind of fascinating thing about it is that the actual thing that makes it so harmful is also the thing that allows it to be this tool for good. So for example, ionizing radiation has the ability to kill cells, right? And in the process of destroying cells, you can, interfere negatively with the normal biological functioning of a body. But on the other hand, if those cells that you're killing are bad cells, like let's say cancer cells, then radiation becomes this amazing tool that, if focused and contained in an area that it has cells that are doing harm to your body, it could destroy them, and consequently has become an immeasurably important tool in the fight against cancer. And any of you that pursue oncology will no doubt be using radiation as a tool to save lives at some point. So this makes this whole concept of radiation very fascinating and compelling, right? It's both harmful and necessary to save lives, and at the same time invisible and almost magical. So we should begin with the question of what the heck is ionizing radiation? Now, radiation itself isn't necessarily so harmful unless it's ionizing. And many of you know from chemistry that ionizing really means that you have provided enough energy to an atom where the electron gets ejected. Okay, so the electron gets so much energy that it's more energy than is held in the ground state, and it's able to fly off, right? Almost like, if you give a rocket enough energy, it'll be able to escape the gravity of a planet, right? Now, what happens once an electron flies off of an atom? Well, now you have an ion. And as soon as you have an ion, things are unstable because things can begin to react, right? Now there's electrostatic attractions and interactions between molecules. These instabilities that happen in ions as a result of ionizing radiation are what cause potential cell death, potential changes in genetic structure, and frankly, the collection of biological harmful symptoms that happen as a result of ionizing radiation. Okay? So that, in a nutshell, is why radiation is so dangerous, right? It is ultimately this ability to provide enough energy to atoms and molecules in cells such that it creates these ions that create instabilities in these cells that ultimately can lead to cell death. All right? Now, in exploring how we quantify and measure these effects, there is a series of 4 concepts which I will introduce to you in the next video.